Okay, so Deuteron bound state we were studying, and then we assumed that it is a central square well potential, the interaction between neutron and proton in Deuteron. We assumed it to be a square well potential, and with that and range also we assumed R naught 2.1 femtometer, which is typical interaction range for nucleons. And then we found that if we take this potential V is equal to 0 for R greater than R naught and V is equal to minus V naught for R less than R naught. This is called square well potential. In terms of R, if you plot, it looks like it is going and then it is like a well and then it is coming back. This is V equal to minus V naught, this is V equal to 0 and this point is R naught. Then we wrote Schrodinger equation assuming L equal to 0, right. We wrote equation for L equal to 0 because we are only looking for the bound state, ground state energy, and Deuteron only has one bound state, no excited states. For that energy to be minimum in a central potential, L should be 0 because it always adds to the energy L plus 1 h cross square by 2 m r square. And then wave functions we wrote. So, inside the wave function was u1. u1 was what? A sin kr, and in the second region u2 it was d e power minus gamma r. So, this is for r less than r naught and this is for r greater than r naught. And what was k and what was gamma? What was k?
Under root 2m
Huh?
V naught plus E upon h square.
Good. V naught plus E upon h square. This was k and gamma was
Under root minus 2m E upon h square.
okay. Then we imposed the condition that this has to be the wave function should be continuous everywhere and finite everywhere, square integrable and all those conditions. The slope should be matching, and from that we got a certain relation in this energy, and from there we obtained that this V naught is 36 MeV. So, if it is a square well potential of this type, that means separation between the two nucleons, if that is plotted with some origin, then it is a spherical volume. Inside that the potential is minus V naught, outside that the potential is 0, then that depth of this potential, the difference from outside to inside should be something like this 36 MeV that we had seen. So, now we know that this depth is 36 MeV, and what is the energy of the deuteron E? We have already used that E to get this 36 MeV. That E was minus 2.225 MeV, which is the binding energy of the deuteron. If you supply this much of energy, so they can separate out, right. If that energy goes into the internal structure. Of course, you can give kinetic energy to deuteron and deuteron can be accelerated to very high energies, mega electron volts, that is another story, but to break that neutron and proton apart. So, if this internal structure, if you give this much of energy 2.225 MeV to the internal structure, then they can break apart. So, the energy is this much. So, on this diagram, if I want to draw a line for E, where it will be approximately, this is 36. So, 2, where will be 2? Very close to this top, right, very close to this top. This is 36, half of it will be 18, half of that will be 9, half of that will be 4, half of that will be 2. So, you can see that the energy level is very close to the top of the well, right. If it is slightly above, if it is beyond this line, it will be unbound. this will be unbound. So, it is weakly, very weakly bound. You can see from this diagram itself and these values itself that the deuteron is a weakly bound system. That we had also discussed that on the average for most of the nuclei, binding energy per nucleon is around 7-8 MeVs. Here it is only 1.1. It is weakly bound system. Here also you can see that it is weakly bound system. The energy is, if it is the energy, if it is here, then yes, it is strongly bound, it cannot come out of the well. But if the energy is very close to the top of the well, then it is weakly bound. Another way to look at that weakly bound thing is, let us evaluate the wave function little bit to some extent using these expressions here. So, you have k and you have gamma. So, let us calculate this k. How much is k? You have calculators?
Yes, sir.
Okay, take it out. So, let us calculate this k. K is given here. K is equal to square root of 2m V naught plus E over h cross square. And what is this m? M is mass of proton or mass of neutron divided by 2. In fact, it is mp into mn divided by mp plus mn, reduced mass of that system. So, taking the two to be almost same, this m is this. So, h cross square by 2m is h cross square by mass of proton. You can put the values, but let me tell you, this will turn out to be 41.3 MeV femtometer square. The units will be energy times length square, h square by mp, because this is k is 1 by length, right, k is 1 by length, this is in MeVs. So, this quantity is MeV femtometer square. So, MeV will cancel out and this will be 1 by femtometer, which is 1 by length. So, in this unit of MeV femtometer square, the value turns out to be 41.3 h cross square by 2m. So, this k is equal to square root of V naught plus E. How much is V naught plus E? V naught is 36 MeV and E is minus 2.225 MeV. So, it is 36 minus 2.225. So, that is V naught plus E, MeV will cancel out, divided by h cross square by 2m, which is 41.3. So, these many Fm inverse. How much is this? Can you tell? (36 minus 2.225).
Point is 9042.
Right, 0.9042. So, let us say 0.90. Okay. So, let us calculate the sign of Kr at the edge of this well, right. Inside the wave function u, that this u, your wave function is u divided by r, but let us calculate this u. U is a sin Kr. So, at the edge of this well, r equal to r naught, how much is that sin Kr? Sin Kr naught, this is sine of 0.9 and into 2.1. Femtometer and femtometer inverse cancel out, k is 0.90 femtometer inverse and r naught is 2.1 femtometers. So, it is just sine of this. How much is this? Sine of 1.9 radian, remember, not degree, it is not 1.9 degree, 0.946, 0.95. Okay. And where is the maximum of the sin Kr? The maximum of the sin Kr will be, sin Kr is 1 when Kr is how much? Pi by 2, that is 1.57. Okay, that is, and what is r? R is equal to, or okay, fine, 1.57 divided by k. K is 0.9. How much is this?
1.744.
1.744. okay, femtometers. So, now look at this diagram. This is 2.1 femtometers, this point is 2.1 femtometer, this is 0, 1.74. So, 1 is somewhere here, 1.5 is somewhere here, 1.7 will be close to the, let me draw a bigger diagram. Suppose this is the potential, this is 2.1, this point is 2.1 femtometers, okay. 1.7 will be somewhere here, this is 1, 1.5, 1.75 will be somewhere here. So, it is maximizing here, this wave function if you are plotting, it is maximizing somewhere here, u if you plot sine curve, it is maximizing somewhere here, sine kr at pi by 2, kr equal to pi by 2, it is maximizing, and after that it is decreasing, but you get this 2.1 femtometers just after this, close to this. So, in this much of distance it has to fall, and it will fall from, if this is 1, it has to fall to 0.95 only, 5%. Okay. So, this edge is almost coming like this, 5% it is falling, and after that it is falling, but not according to this function sin kr, it is falling according to the function d e to the power minus gamma r. Now, you are in the second region. So, let us evaluate this gamma also. So, this thing I can erase, and let us calculate gamma. So, keep your calculators ready. Gamma is square root of minus 2 m e over h cross square, and that is E is minus E is 2.225 and divided by h cross by 2 m is 41.3 femtometer inverse, or 1 by gamma. Let us do it 1 by gamma. 1 by gamma is square root of 41.3 divided by 2.225 femtometer. Tell me what is this? 4.308, so 4.31. Now, you know, if you have a function e to the power minus gamma r, then this 1 by gamma is the length in which it is decreasing by the factor e, 37%, 1 by e. Okay. So, this is a characteristic of how steeply the exponential is decaying. So, that 1 by gamma gives you a scale that all right, it is significantly decreased up to this. Okay. So, that is 4.31. If this is 2.1, 4 will be somewhere here. So, by the time it reaches here, it will be reduced to 1 by E. E is 2.73 something, all right, 2.73 something. So, it is reduced to 37% somewhere here, slow decrease, right, slow decrease. So, it will be almost going like this. This is exponential decay. Characteristic length is that 4.3 femtometers. By that time it reduces to 37%, 1/3, it becomes 1/3 of that. So, it is a slow decrease. So, what do you understand from here? Most of the time wave function, lot of wave function is outside the well, right, and it goes to large distances outside the waves. So, you can say that for a very significant time, this neutron and proton, they are separated by a distance which is much larger than the range of nuclear interaction. Of course, for some time it is also in the nuclear range. So, overall it is a bound system, but it is a very weakly bound system. Most of the time it is not interacting through that nuclear attraction, because it is outside that 2.1 femtometer region. All assuming that it is a square well potential and sharply goes to 0 and all those things. But qualitatively the fact remains that yes, the deuteron is a very weakly bound system. The wave function extends beyond the nuclear range of interaction, and therefore, you do not expect any excited state and so on, which is actually the observed thing. Hardly it is bound. So, any energy, any extra energy given, it will be just it will become unbound. Okay. So, these things we can understand from the measured value of energy. We know this energy, therefore, we could deduce that it is 36 MeV deep potential, and from there we did all those calculations to understand how weakly it is bound and all those things. So, one experimental parameter that the energy of deuteron is minus 2.225 MeV has given some picture of deuteron. There are many other experimentally measured parameter of deuteron, and from there also we can get some knowledge about the interactions. So, one is there are many, I will go one by one. One is angular momentum and parity, and then we will have magnetic moment and quadrupole moment. Those things are also measured, we will talk about that, but first the angular momentum. Now, in a nucleus you will have certain number of protons. Deuteron you have only one proton and one neutron, but in a nucleus in general you will have several protons and several neutrons, and you have two kinds of angular momenta. One is orbital angular momentum, which you denote by L, the letter L, and another is a spin angular momentum, which you denote by S. And for each nucleon you will have L and you will have S. And if there is some interaction between them, then this L and S will combine to a final angular momentum for that nucleon, which we call J. So, L plus S will become J. So, orbital angular momentum and spin angular momentum makes a net angular momentum for that nucleon. But then there are many nucleons. So, you will have J1, J2, J3, J4 and so on. All these things will also couple if there are corresponding interactions. They will also couple and give you a final total angular momentum of the nucleus, right. So, all those J1, J2 these things will also couple, and it will give you a final total angular momentum of the nucleus. So, that is denoted by the letter capital I, and it is given a name nuclear spin. So, do not confuse that it only corresponds to the spin angular momentum and not orbital angular momentum. It is the total angular momentum, it is called nuclear spin. Nuclear spin of this particular nucleus is this much, right. So, that is total angular momentum of the nucleus. That is one parameter which can be experimentally measured. Another thing is parity, that is also experimentally measured, and parity in fact tells you that the space part of the wave function will also have space part and spin part. Okay. We were talking of space part only. The wave function space part, whether it is symmetric about reflection in origin or it is antisymmetric about reflection in origin. It so happens that in nucleus it is either symmetric or antisymmetric. We say that parity is definite. So, the wave function, the space part of wave function, say phi r, r theta phi, space part of the wave function. Consider this, if you have a point say here, this point which is at position vector r, reflect it in origin, you will reach somewhere on the other side same distance, and this position vector will be minus r. So, that is reflection in the origin. So, same line, you extend same line on the other side, and then at the same distance you locate the point. So, this point is just reflection of this point in this origin. Okay. So, here you have this point itself, if you write this as r theta phi coordinates, spherical coordinates. So, what are the spherical coordinates here? Same distance from the origin. So, r is same, right, and the theta from z axis, what is that angle? So, that has reflected. So, from here it is this and now it is this. So, this was theta and now this is theta. So, how much it is? This whole thing is pi, and this thing is theta. So, it is pi minus theta. Okay. And phi, what happens to phi? Phi goes to phi plus pi. Okay. Then if this phi r happens to be equal to phi minus r, the space part of the wave function here and space part of the wave function here, if they happen to be same, equal, then we say that the parity is even. And it is denoted by positive parity, pi. For parity we write pi. So, pi is positive plus. And if this space part phi r is equal to minus of phi at minus r, the wave function here and wave function here are negative of each other, just multiply by minus 1 and you get the other wave function, then the parity is called odd. Parity is odd, and we write this as pi is negative, minus. And this is related to the orbital angular momentum quantum number L. This theta phi part, if it is a central potential, you know that theta phi part will be y lm theta phi. At least for central potential we know the theta phi part of the wave function. For any central potential, square well or any central potential which does not depend on theta phi, the wave function will depend on theta phi according to that capital Y L m, spherical harmonics. So, that L is there in this wave function, and that L is directly related to this parity. If L is even 0, 2, 4, then your parity is positive, and if L is odd, then parity is negative. For deuteron, both this total angular momentum, that is nuclear spin, and the parity are measured and are known.
So, here we can have mixed parity?
For nuclear wave function, the parity is definite. For all nuclei, the parity is definite. There is a reason for it, maybe we will talk about that. But for all nuclei, the parity is either even or odd. Parity is definite. If the Hamiltonian of your system commutes with parity operator, then parity is definite, and the nuclear Hamiltonian happens to follow this rule. So, all nuclei will have definite parity wave functions. That definite parity can be positive and can be negative. For deuteron, these things are measured I is equal to 1 and parity is positive. So, we write it as 1 plus j pi. So, the I pi. So, I is 1 and pi is plus. So, that is deuteron. So, let us see if we can learn something from this. Now, if we look at the deuteron, you have two nucleons, okay, and the two nucleons, one is proton, one is neutron, and they will have S1 spin quantum number is half, SP let us say SP is half, and Sn is also half. Any proton in the whole universe, any neutron or any electron, they are all spin half particles. Spin half particles means that quantum number S is half, but quantum number S is half. This corresponds to different states. If you look at the square of the angular momentum, square, this is physically measurable quantity, square of spin angular momentum. You write it S square. That S square is, this is half, that means it is half into half plus 1 into h cross square, that is 3 by 4 h cross square. So, angular momentum square, spin angular momentum square, if you measure this for any electron, okay, for any proton or any neutron, it has to be this. But then if you look at the z component, that is another physically measurable quantity Sz. It can have two values, it can have the values h cross by 2 or minus h cross by 2. You know this? If S is half, if this is quantum number is half, then it can be half into h cross minus half into h cross. For any angular momentum, similar thing will follow. For orbital angular momentum also, if L is 1, small l is 1, orbital angular momentum quantum numbers are always integral. Then it will be, it can have three values, 1 into h cross, 0 into h cross, minus 1 into h cross. If L is equal to 2, then it can have 5 values, 2 into h cross, 1 into h cross, 0 into h cross, minus 1 into h cross, minus 2 into. If you are talking in terms of some total angular momentum j, if j is 3 by 2, so that Jz will have 4 possible values, 3 by 2 h cross, 1 by 2 h cross, minus 1 by 2 h cross, minus 3 by 2 h cross. So, from that quantum number to negative of that, it goes in units of h cross. Okay. So, these are the possible values. For this we will put a symbol up, and for this we put a symbol down. So, if you have two nucleons, one proton and one neutron, you can decide that first you will put the symbol for proton, another next you will put the symbol for neutron, and you can write this into a ket. So, if you decide that first arrow is for proton and second is for neutron, so this tells me that proton has Sz equal to plus h cross by 2 and neutron also has Sz is equal to h cross by 2. Then you have another possible state where it is like this. So, proton has this z component of angular momentum, spin angular momentum, whereas neutron has this minus h cross by 2 down, spin down, call it spin up, spin down. Similarly, you can have a situation where this is up and this is down. You can have a situation where both are down. This is when the two spin angular momenta are not coupling to each other, they are independent. Is there, proton is there, it has its own S1z, and then the other neutron is also there and it has its own S2z. So, anything can be up, anything can be down, but if they couple, if the two spin angular momenta couple, and here since the orbital angular momentum we are taking it to be 0, central potential, lowest energy. So, your total nuclear spin is resulting only from the coupling of these spins. Okay. So, now if S1 and S2 couple to make a final capital S, right, a final capital S, Sp plus Sn. First thing, half plus half, this is half, Sp was half and Sn was half. So, the possible values of S are half plus half, that is 1, and half minus half, that is 0, and in steps of 1. So, only two possible values, two angular momenta, half and half, S1 equal to half, S2 equal to half. if they are adding, if they are coupling to produce a final angular momentum coupling these two S1 plus S2, that final thing can be either half plus half or half minus half. The general rule is, if you are coupling two angular momenta J1 and J2, it can be J1 plus J2, it can be J1 minus J2, and all the numbers in between, if you go in steps of 1, decrease by 1, from J1 plus J2 to J1 minus J2, you go in steps of 1. So, all those things are possible. So, here half plus half to half minus half in steps of 1. So, you only have these two values 1 and 0. So, capital S can be 1 and capital S can be 0. If capital S is 0, capital SZ is equal to S1Z plus S2Z or SPZ plus SNZ. Okay. The Z components add. S is SP plus Sn, the Z components also you can write Sz is equal to SPZ plus. So, for S equal to 0, Sz can only be 0, right. If the angular momentum is 0, that Z component has to be 0. If it is 1, if S is equal to 1, then the Z component can be H cross 0 minus H cross. This angular momentum rule applies here. This is also angular momentum, spin angular momentum. So, if the quantum number is 0, then the Z component is just 0, and this Sz0 means this whole thing is 0. So, one has to be plus half and one has to be minus half, one has to be spin up, one has to be spin down, but then there are two possibilities, right. This can come from up, down and down, up. First arrow is for proton and second arrow is for neutron. So, this state will also give you Sz equal to 0 and this state will also give you Sz equal to 0. This state Sz equal to 0 is a combination of these two, and that combination is you put a minus here and 1 by root 2 outside. This is the state where S equal to 0 and Sz equal to 0. Okay, S equal to 0, Sz equal to 0 is this state, only one state. But if you look at S equal to 1, S equal to 1, then Sz can have three values. Sz can be H cross, Hz can be 0 and it can be minus H cross, right. You remember hydrogen atom L equal to 0, then L equal to 1, 2p state. So, for L equal to 1, that Ml can be 1 0 or minus 1. So, similarly here this S equal to 1. So, Sz the quantum number will be 1 0 minus 1 and times H cross. So, so you have three states, three possible states. One is when Sz is H cross, and remember Sz is Spz plus Snz. So, if this is H cross, both of them has to be H cross by 2 plus H cross by 2. It can be H cross by 2, it can be minus H cross by 2 for a single nucleon. So, if the total has to be H cross, both of them should be in plus H cross state. So, you have let us say S equal to 1 and Sz is equal to H cross. Corresponding to this, what will be this wave function? It has to be this one. This is also H cross by 2, this is also H cross by 2, and when you add these two you get H cross. Similarly, writing state for S equal to 1 and Sz is equal to minus H cross, this is also easy. What it should be? Both down, because minus H cross you will get when each of them are minus H cross by 2 minus H cross by 2. It can only be either plus h cross by 2 or minus h cross by 2. So, to obtain this minus h cross, both of them have to be minus h cross by 2, and to obtain this plus h cross, both of them have to be this. But then there is yet another state which is s is equal to 1 and sz is equal to 0. And here one has to be up, sz is equal to 0, and one has to be down. So, once again it will be combination of these two, but different from this. This is s equal to 0 and this is s is equal to 1, although sz is same. So, this state is different from this state. In fact, they are orthogonal, because at least one quantum number is different. So, this combination is 1 by root 2 and then up down plus down up. Okay. So, you have 4 states, again 4 states. Here also you had 4 states when there was no coupling. Here also you have 4 states when you have coupling, and the 4 states, one here with capital S equal to 0 and 3 here with capital S equal to 1. All right. So, you again have 4 states there. Now, if the nuclear interaction is independent of spin, nuclear forces are independent of spin, then it does not matter whether it is up or it is down, equally probable. So, out of these 4, 3 corresponds to capital S equal to 1 and 1 corresponds to capital S equal to 0. So, 75% probability is that it will couple to capital S equal to 1, and 25% probability is that it will couple to S equal to 0. What is the measured value telling me? Capital I is equal to 1 and orbital angular momentum is 0. So, what is capital S? The orbital angular momentum and this spin angular momentum, I am talking of Deuteron as a whole, should couple to capital I. Capital I is 1 and this L is 0. So, this S has to be 1. So, Deuteron bound state must be S equal to 1 if we are thinking that it is central potential and L is 0. It is not 75% times 1 and 25% times 0, it is 100% times 1, right. Even if I go for non-central potential, you will find, I will just do it in a minute, that capital S has to be 1, capital S is never 0 in Deuteron bound state. Okay? So, that tells me that nuclear interaction is spin dependent, it favors capital S equal to 1 and it does not favor capital S equal to 0. So, the nuclear interaction is different for S is equal to 1, capital S equal to 1 and capital S equal to 0. I will just do that even if it is a non-central potential, this statement remains valid. Okay. So, let us look how we can get this capital I equal to 1, what are the possible combinations. This capital I is coming from L and S. So, S can be 0 or 1. So, if S is equal to 0, if this is 0 and this is 1, so what you should have here? L, for L what you should have? S is equal to 0. So, this L has to be 1, that can give you I is equal to 1. Right. If S is equal to S equal to 0 and L is equal to 0, what you will get? I equal to 0, 0 plus 0 is 0. If S is equal to 0, L is equal to 2, what will you get? I equal to 2. And if you increase L further, I will increase. I am only interested in this I equal to 1. So, with S equal to 0, you can have L equal to 1, then you will get I equal to 1. Okay. Now, look at S equal to 1. If S is equal to 1 and this L is equal to 0, you will get I equal to 1, that is fine. If S is equal to 1 and L is equal to 1, what will you get? 1 plus 1, 2, 1 or 0. 1 and 1, when they couple they can give 2, 1 or 0, from 1 plus 1 to 1 minus 1. And if it is 2, what you can get? 3, 2, 1. So, you can get I equal to 1 in all these combinations. Can I go ahead? If S is equal to 1 and L is equal to 3, then 4, 3, 2. 3 plus 1 is 4 and 3 minus 1 is 2. So, 4 to 2. So, now I will not get capital I equal to 1. So, the possibilities are here, the possibilities are here, the possibilities are here, then possibility is here. Here L is equal to 1, right, L equal to 1, but then L equal to 1 will give you an odd parity. And Deuteron parity is again experimentally measurable quantity, measured quantity, and that is plus. Deuteron parity is plus. So, since this will give you pi equal to negative, so this is out, this is out. The experiments do not suggest that it can be a possibility, right. So, the measured parity is positive, whereas this combination will give me negative parity L equal to 1. And this is anyway I equal to 2 I am not interested, I equal to 0 I am not interested. So, with S equal to 0 you cannot get I equal to 1. So, the S has to be 100% 1, not 75%, 100% 1. S cannot be 0, right. The measured values say that S cannot be 0. So, S has to be 1. Now, in this S, this part we will cross out, L equal to 1 is not allowed, and here anyway we are not getting I equal to 1. So, at best I can have a mixture of L equal to 0 and L equal to 2. Okay. So, if it is a non-central potential, in central potential L is fixed. If it is a non-central potential, then you can have different values of L coming in the energy eigenfunction, right. In the same level, same state, you can have a combination of angular momenta if it is a non-central. Even if it is a non-central potential, the combination must be with L equal to 0 and L equal to 2. That is possible with capital I equal to 1 and parity positive. Okay. So, it has to be spin dependent part. The Hamiltonian must have a spin dependent part. One way of putting that spin part in the potential is adding a term which is which contains S1 dot S2. So, SP dot Sn. From atomic physics we are familiar with this kind of interaction, LS interaction and all that thing. So, some spin dependent potential depending on R and then SP dot Sn. You can have this type of term added to the main central potential that you had done. How that makes a difference? Now, what is your observation? Suppose the Hamiltonian is different, the interaction potential is different for capital S equal to 1 and capital S equal to 0, is spin dependent. So, in which case it will be more attractive, capital S equal to 1 or capital S equal to 0, in which case it will be more attractive. From the observations that we have done here, you can answer this question. Suppose you have a potential which corresponds to capital S equal to 0 and a potential which corresponds to capital S equal to 1, right. Of these two, which one is more attractive? The force is stronger, attractive force is stronger, or the depth of the well is deeper, capital S equal to 1 or capital S equal to 0? It has to be capital S equal to 1, because the Deuteron bound state corresponds to capital S equal to 1, right. That is what we are discussing. So, capital S equal to 1, the potential is able to keep this Deuteron bound. Capital S equal to 0, no. you do not have a bounded state corresponding to capital S equal to 0. So, capital S equal to 0, if it is a square well potential, the depth will be less than 36 MeV, it is not able to bind it. Whereas, capital equal to S equal to 1, the depth is just able to bind it, okay, just able to bind it. It is a very weakly bound system. So, potentials are different. You can make a calculation of this SP and Sn. You have S is equal to Sp plus Sn, and from here you can write S square is equal to Sp square plus Sn square plus 2 times Sp dot Sn, and from here you write Sp dot Sn equal to S square minus Sp square and minus Sn square and divided by 2, that is S square minus Sp proton. So, for a single proton, Sp square is always half into half plus 1 h cross square, that is 3 by 4 h cross square. So, this is 3 by 4 h cross square, this is 3 by 4 h cross square neutron. So, this is minus 3 by 2 h cross square n by 2. So, if S is equal to 1, this quantity Sp dot Sn is equal to, if S is equal to 1, then this is 1 into 1 plus 1 h cross square, this is 2 h cross square. How much is this? And if S is equal to 0, then this side is, this is 0. So, it is minus 3 by 4. So, you can see that this is this gives you a spin dependence. For capital S equal to 1, it is this term is this much. For capital S equal to 0, this term is this much. So, if you add a term like this in the potential, your potential will become spin dependent, okay. And then depending on, you will put proper sign, positive, negative, and all those things are dependence. So, that S equal to 1 potential should go deeper and S equal to 0 potential should go up, and then you have two different things here, right. After this angular momentum of parity, the other experimentally measured quantity is magnetic moment, Z component of magnetic moment of deuteron. That is also experimentally measured quantity, and that is mu is mu of deuteron, Z component of mu of deuteron. Measured value of magnetic moment of deuteron turns out to be 0.8574, what we call nuclear magneton. You know what it is? Nuclear magneton. Nuclear magneton is E, this is charge on a proton, H cross divided by 2 times mass of proton. This quantity is called nuclear magneton. It has a fixed value, and this value turns out to be 3.1525 into 10 to the power minus 8 eV per Tesla. The unit is eV per Tesla. This is called nuclear magneton. And the measured value of magnetic moment, Z component, when you measure the Z component only. Z component, what is Z component? You apply some magnetic field or something to measure that moment, and that direction itself defines the Z axis in which you are applying the field, magnetic field, or doing something. So, that measured quantity is this. Now, from where this magnetic moment is coming for deuteron or for any nucleus, from where this magnetic moment is coming. So, magnetic moment has a direct relation with angular momentum. magnetic moment is directly related to angular momentum. So, if I do it for a particle, classical particle going in a circle, remember that you must have done this. So, if a charge q is going in a circle of radius r, very fast moving, so that looks like a continuous current, if it goes very fast. So, the angular momentum L is mass of the particle times speed times r, okay, that will be Lz, and the equivalent current is, it is q charge is crossing here, right. So, current, equivalent current is q charge is crossing divided by time. In 1 second or unit time, how many times it is going? After what interval the q charge is coming? One time period, and that one time period is 2 pi r divided by v. 2 pi r distance it will go with a speed v. So, the time taken will be 2 pi r by v. So, every 2 pi r by v q charge crosses, the point comes and crosses, and it is very fast, remember. So, in that case this will be like I is q by t. So, this will be the equivalent I, and the magnetic moment mu, let me write z, magnetic moment mu z will be I times pi r square, the usual electromagnetism formula, and so pi r square. So, q v r by 2. If you put mass in denominator and numerator, it is q divided by 2 m times angular momentum. Okay. Now, this equation turns out to be accurate in quantum mechanics also, if you are only talking of orbital angular momentum, right. If you are talking of orbital angular momentum, this formula is still correct. So, for electron for example, or proton, this will be charge q will be just E, and m will be mass of that particle. If it is electron, it is mass of electron, if it is proton, it is mass of proton. So, mu L z, what I am writing this L, I am talking of the magnetic moment corresponding to orbital angular momentum, not the net magnetic moment. So, that will be still given by this e to the e divided by 2 m and then L z, okay. Or you can write this as this is now mu n. If it is proton, it is mu n divided by h cross. Remember, this is nuclear magneton. So, E by 2 m, I am talking, let us talk of proton. So, this is E divided by 2 mass of proton. So, E divided by 2 mass of proton is mu n, all right, mu n, this is the thing, the symbol for this is mu n here, this mu n. So, this mu n divided by h cross times L z. For neutron, what will happen? For neutron, what is mu L z? You put neutron mass here, and what do you put for the charge? Neutron is negatively charged, neutron is 0 charge. So, neutron will not have any magnetic moment corresponding to orbital angular momentum, right. This magnetic moment corresponding to orbital angular momentum will come only from proton, not from neutron, okay, right. So, we will take it from here.